Hello students. Today in this video, I will explain a very important concept that how does gravitational field strength varies inside the earth. Okay. So what is G at the center of earth? So after watching this video, you will be able to understand that the variation of G inside the planet, any planet or earth is not similar to the variation of G outside the planet. As you move away from the surface of the planet, gravitational field strength or gravitational force decreases. Uh, you know that it is inversely proportional to r square, but you don't know what is the gravitational field strength inside the surface of a planet. Okay, so you know that gravitational force between two masses is given by this formula. What's the formula of gravitational force? That is G m1 m2 over r square. So gravitational force is proportional to the product of masses and inversely proportional to r square. Does this mean if we put r equal to 0 at the center of the planet, r will be 0? Okay. If I bring this mass on the surface of the planet, okay, let's say this is the surface, and if I want to find the force between this mass and this mass, will the force become infinity? Does this mean if you put r equal to 0, the mathematical relationship states that the force should become infinity? So we have to understand that this is not the case. The force is, according to this relationship, force is infinity at r equal to 0. So I will explain that this relationship is, how does this relationship is valid inside the surface of the planet. Okay. So suppose you are at the surface of this planet, this earth having the mass m, and as you move inside, we have a tunnel inside the earth. So as you move down, the gravitational, how does the gravitational force on you changes as you move from the surface of earth to the center of earth? Okay. So over here you can see, as you move inside the earth, the mass of earth below you and the radius both changes. Okay. So we will understand this expression, the concept, using this diagram. Let's say you have, look at this diagram. This is earth, and we have made this inner part of this earth hollow. We have removed this part of earth, the inner part of this earth. Okay. So we are left with only this mass, this region. Okay. So let's say you stand at the center of earth. So what will be the net force on you? Will there be any net force? Will you experience any net force? Okay, let me explain. You have this mass on this side, and due to this mass, you will experience gravitational force in that direction. And you have equal mass on the other side. Okay. So due to that mass, you will experience force in that direction. As on the other hand, you have the mass on the upper side, so you will experience force in that direction. You will experience force in that direction. So what are you observing? You are experiencing force in all direction, and the forces are equal in magnitude. So as a result, net force on you is 0. Net force being vector quantity, so net force on you is 0. So this means that if there is no net force on you, we know that gravitational force is mass time gravitational acceleration. So if there is no net force, that means that there is no gravitational field strength. So inside this, in this hollow region, the gravitation inside this hollow region, the gravitational field strength will be 0. So G will be 0 at any point inside this hollow region. Okay. So let me clarify one more thing. Suppose you are standing somewhere at this point. So the net force on you will also be 0. This force is smaller in magnitude, this is larger in magnitude. You are also experiencing force in that direction, in all directions. So overall combined effect of the force will be 0. So if you are at any point, somewhere here, somewhere here, here, you will experience no net force. So what is the assumption over here? We assume that the density of this part is constant, that is not changing. So if you don't assume this, if you don't assume the density to be the uniform, then the net force inside that planet will not be 0. Okay, so net force in this region is 0. This means that you are not experiencing any force due to the upper ring of the mass. Okay. So now, as you move down, come to this diagram. As you move down into the earth, the mass, let's say you are standing somewhere here. You are standing somewhere here. So you are not experiencing any force due to this mass, due to the ring of this mass. You have now two masses. One is this mass ring, and now this inner part is not hollow. Okay, and you are standing somewhere inside the earth, and the mass below you is capital M, and the mass on the upper side of you is small m. So you are, according to this diagram, you are not experiencing any force due to mass m. You don't feel any net force due to this mass m. So this region of mass does not apply any net force on you. So you are only experiencing force due to this mass. So what happens? As you move down, this radius, both the radius and this mass are changing. So your mass, the force on you is G. Let's say your mass is M1, and the mass that applies force on you, the part of mass of Earth is capital M over R square. So as you move down, both of these quantities are changing. Okay, both of these quantities, like this mass and this radius, are changing. Okay, so now we have to look how mass and radius are changing. So we have to convert this expression into in terms of a single variable. If both quantities are changing in a mathematical formula, then we can't predict or see what is happening. Is the force increasing or decreasing? Math is decreasing, and distance is also increasing. So this R has increasing effect on the force, and the mass has decreasing effect on the force. Okay. So this means that this relationship, the gravitational field strength, is, G m over r square. Gravitation field strength, that gravitation force per unit mass, and if you want to find the gravitational field strength at that point, that will be the gravitational force divided by your mass. Okay, so you will get this relationship. Now we see m is also changing, r is also changing. So we have to convert these two variables in terms of a single variable. You know that mass is density is mass over volume. Density is mass per unit volume. Okay. Density of this part we are talking about. So the mass over volume. So as a result, mass will be equal to density into volume. So what is the volume of this? This is spherical part. So the volume of the sphere is, the formula of the volume of sphere is 4 by 3 pi r cube. That is how does mass varies. As you come down, the mass, this m varies with r cube. Okay, mass is directly proportional to r cube. So if I, okay, so I was doing this. I'm sorry, my screen stuck. So G is, I will put the value of m from this equation over here. So I will get G 4 by 3 pi r cube over r square. Now you can see I have converted the expression of G into a single variable, in terms of single variable, that is r. And if I will simplify this r cube over r square, I will get 4 by 3 pi g r. So what are you observing? That is G is, that's great. G is directly proportional to R. Inside the planet, gravitational field strength, this 4 by 3 rho G is constant, then we can say G is directly proportional to R. Okay. So this relationship is valid inside the surface of Earth. So what is G at the center of Earth? That's great. At the center of Earth, R will be 0. So G will be 0. So gravitational field strength at the at the center of Earth will be 0. You will experience no net force, no force at the center of Earth. And as you move away from the center of Earth to the surface of Earth, as you move from here to, let's say you are standing somewhere here, and you move from here to the surface of Earth, the gravitational field strength will increase, and it will becomes maximum at the surface of Earth. Then after the surface of Earth, the variation of gravitational field strength is inversely proportional to r square. because this mass is not changing now. So the only variable that changes away from the surface of Earth is the distance from the center of Earth. So gravitational field strength is inversely proportional to the square of distance from the center of Earth. But inside the Earth's surface, gravitational field strength varies differently. That becomes zero at the center of Earth, and that increases to the surface of Earth till the surface of Earth, and then it decreases. Okay, so let's say you are here and you move inside, you make some tunnel inside the Earth, and you move from one end to another end. What will happen? G is maximum at that point. Gravitation field strength decreases, and it becomes zero at the center of Earth. Then gravitation field strength will still increase, and it will become maximum at the surface of Earth. Direction of gravitation field strength is always toward the center of Earth. So this is how the variation of G is inside the surface of Earth. But we have assumed that the mass of the density of Earth is uniform and Earth is in the form of a spherical object. Okay, these are two assumptions. So now I want to plot the graph of G inside and outside the surface of Earth. So let's say this is G and this is mass of Earth. This is Earth. You can see from here, this is Earth and this is surface of Earth. Till the surface of Earth, the gravitational field strength will increase. So it will have a straight line relationship till the center of Earth. Then G will decrease. It will follow inverse square law. So as you move from the center of Earth to the surface of Earth, G increases, it becomes maximum. Then G decreases as you move away from the surface of Earth. Now one more question. If you make a tunnel inside the Earth, let's say you, as we discussed in this example, if you make a tunnel inside Earth and you drop some object from here, from this point, okay, you drop some object. I don't wish you should, you go yourself, but you draw some object from here. So what will happen to this object? It will experience force towards the center of Earth, and that force is maximum over here, and that force then decreases, and it becomes zero. So at the center of Earth, then as you cross the center of Earth, the force on you becomes in the opposite direction, so you will become slow. So from here to here, you will become slow, and due to inertia, you will go, the direction of velocity is towards down. This is direction of velocity, but the direction of net force is up. So you will, if the velocity and acceleration are in opposite direction, your speed will decrease. Okay. So when you will reach at this point, the force on you will become maximum, and after that, the force decreases. So as a result, this object will oscillate between these two positions. This object will oscillate between these two positions. So if you make tunnel between Earth, in the middle of Earth, and you drop some object, this object will oscillate between position A and B, and this is similar to the motion of simple pendulum. Let's say you have this mass, and as you drop from here, this mass will go here, and at this point its velocity will become maximum, and as it moves from here to here, the direction of net force is in this direction, then direction becomes in this direction. So the mass oscillates between these two positions. Okay. So this is the end of that video. We discuss in that video how the gravitational field strength and the force on mass inside Earth is varying, and what is the gravitational field strength inside the at the center of Earth. So this relationship is valid inside the surface of Earth, and that relationship is valid Gm over R square. Gm over R square away from the surface of Earth. So as you move away from the surface of Earth, G decreases, over here, G decreases. And as you move from here to here, G will increase. Okay.